In this video, we're going to look at equations for how we can convert back and forth between Cartesian coordinates and spherical coordinates. So we're not going to go through all of the trig details, but I want to draw the figure just so you can kind of be thinking about it or kind of have at least some idea of where we're getting this stuff. So let's say we have some point here that we're representing in spherical coordinates. So as we've seen before, let's say it's in this first octant, so positive x, positive y, positive z. Well, let's draw sort of a line down to our, well, actually, let me just make this solid. Let's draw a line down to our xy plane. Let's say it's somewhere about there, so that's in our xy plane. Of course, we're going to have a distance r from the origin to this point, so that's part of our spherical coordinate system. If we have also some x and y associated with this point, so something like this. And of course, we also could talk about a row that's associated with that. Let's see, we don't want to erase, but let's put in a row here. And so basically what we have then is, let me label some things here. So we have two right triangles. We have a right triangle in our xy plane, where this angle here is our phi, the same as we saw with our cylindrical coordinates, but this is also defined in our spherical coordinates. And of course, this distance here would be our x, this would be our y, and this would be our rho. Now for our once we sort of come out of that xy plane, we have our z, which is bringing us up to our point. And then we also have this distance r from the origin to the point. And we have this angle here, which is our angle theta. And of course, this is a right angle over here as well. So basically, we have two right triangles which we can use to relate all of these parameters. And in this case, our rho is just going to be sort of an intermediate parameter because rho doesn't show up as a key parameter in Cartesian or spherical. But ultimately, we want to be going from x, y, z. So let me say, let's do highlight in green. So we have x, y, z, and we want to be converting that to our spherical or from our spherical, which is going to be our r, theta, and our phi. So that's sort of the shapes that we can use to relate these two. And again, with our vector-to-vector transform, which we're going to talk about in a little bit, the ultimate idea is we're relating our unit vectors to each other. Again, we're not going to go into a lot of details on that, but if you want to see more of that or sort of more details of the derivation, you can look on pages 37 to 38 of the textbook, and of course let me know if you have any questions. But let's go ahead and just sort of write down the end results, starting with our point-to-point transforms. And again, as the name implies with our point-to-point transforms, we're saying we have a point in Cartesian coordinates and we want to represent it now in spherical coordinates or vice versa. So we're just talking about a point. So let's say we have a point in Cartesian and we want to go to spherical. So we could say that our r is equal to the square root of x squared plus y squared plus z squared. Our theta, which is our second key term, is going to be the inverse tangent of square root of x squared plus y squared in the numerator, so that's equal to rho, so we've kind of used rho as an intermediate value, divided by z. And then finally, our phi is going to be, like we saw before, is just the inverse tangent of y divided by x. So let me move this out of the way a little bit so we can box this in. Let's move this down. So this is going to be, again, if we were going from Cartesian to spherical. So this is Cartesian to spherical. Let's say we wanted to go the other way though. So if we are going the other way, we can say x is equal to r times sine of theta cosine of phi. Y is equal to r times sine of theta sine of phi. And our z is just equal to r cosine of theta. So we get something that looks like that. And so again, this would be if we were going from spherical to Cartesian. So the next type of transformation that we can have, as we talked about with our previous video, is vector-to-vector transforms. And essentially, again, here all we're doing is relating sort of our components in one to components in another, and we derive these equations using the relationships between our two sets of unit vectors. Again, I'm not going to go into details, but you can see pages 37 and 38 in the textbook for that. So first, let's say that we have our Cartesian, and we want to find our spherical. So we want to find AR, A theta, and a phi components, so our spherical components. So our matrix is going to be still a 3 by 3 matrix. I'm going to leave myself a little bit more room because our components are going to be a bit longer. And we're multiplying this by AX, AY, and AZ, so our Cartesian components. So the trig is a little bit harder to follow, and actually let me give myself a little bit more space here. Let me just scoot that over. But what it ends up being, sort of our end result, is in our first row, for our first term, we have sine of theta times cosine of phi. Our second term is sine theta sine phi. Our third term is cosine theta. Second row, we have cosine theta cosine phi. Second term, cosine theta sine phi. And then finally, negative sine theta. And then for our third row, we have negative sine of phi, cosine phi, and 0. And again, this isn't something that you would be expected to memorize, but just something you should know how to use and have available to reference for exams or homework. So again, this is if we were going from Cartesian to spherical. But just like with our previous video, we note that in this equation we have our theta and we have phi in here. And of course that's not part of our Cartesian, so if we only had x, y, and z components, how do we get around that? Well, we can kind of have these little supplemental equations where we can say our cosine phi is equal to x divided by essentially rho, which was square root of x squared plus y squared, and our sine of phi is equal to y divided by square root of x squared plus y squared. So same equations that we saw in our previous video when going between cylindrical and Cartesian. Now we also have a cosine theta and sine theta terms to deal with, and so we can get around those by saying that cosine of theta is equal to z divided by r, but instead of writing r, we're going to write it in terms of x, y, and z, which, as we saw previously, is square root of x squared plus y squared plus z squared. Similarly, our sine theta is going to be essentially rho over r, but we want that in terms of x, y, and z, so rho is equal to square root of x squared plus y squared, and our r is equal to square root of x squared plus y squared plus z squared. So I know that's kind of messy, but keep in mind that instead of having to deal with equations that look like this throughout, we could do a transform right away, and then we're dealing with a lot nicer numbers. Again, we'll see this sort of advantage of using the appropriate coordinate system in examples later on in the semester. Okay, so let's finish by looking at how we could go from spherical to Cartesian. So now let's say we have spherical, and we want our Cartesian components, our x component, our y component, and our z component. And again, we're not going to go through the details of this, but we'll copy down the final result. So we have our r component, our theta component, and our phi component, and we're multiplying that by a 3 by 3 matrix. So our first row, we have sine theta, cosine phi, cosine theta, cosine phi, negative sine theta, negative sine phi for that last entry. Second row, we have sine theta, sine phi, cosine theta, sine phi, and then cosine phi for our third row, or our third column, second row. Our third row is cosine theta, negative sine theta, and 0. So this would be the equation we use if we're doing a vector-to-vector transform going from spherical to our Cartesian coordinates. And again, in some following videos, we're going to look at some examples of how we can use these equations.